Lecture 11. In the last lecture, we looked at phase domain technique and we did a brief overview of Fourier series analysis and Fourier series representation. In this lecture, we'll go a little deeper in looking at Fourier series coefficients. We'll go through a circuit analysis using Fourier series, and we'll look at Parseval's theorem. Fourier analysis is the study of the way general functions may be represented or approximated by sums of simpler trigonomic functions. It is named after Joseph Fourier. In the sciences and engineering, the process of decomposing a function into oscillatory components is often called Fourier analysis, while the operation of rebuilding the function from these pieces is known as Fourier synthesis. When processing signals such as audio, radio waves, light waves, seismic waves, and even images, Fourier analysis can isolate narrow bands of components of a compound waveform, concentrating them for easier detection or removal. Several examples are given below. If you recall, we talked about three ways of representing the Fourier series. The first one is the sine-cosine representation. Now, when n is equal to 1, that's the fundamental. And for all other n's greater than 1, those are the harmonics. For the coefficients, a0, an, and bn, how to determine those is given in the equations below. And recall that a0 is the DC offset, or the average value of that representation. Here is the amplitude phase representation, and the coefficients, the Cn and Pn, they are given below. And here's the third representation, the exponential representation, and the coefficient for xn is determined by the equation below. Here are the three representations combined into a single table. Here's an example of computing the coefficients for a square wave. So the coefficients are a0, an, and bn. And since it's a square wave, you can do it piecewise by looking at several pieces of an entire period. In this case, you can break the pieces up into 3 pieces and put them together. Once you've computed the coefficients, then you substitute them into the expression for the representation. In this case, we're using the sine-cosine representation. And when you do that, you have your series of expressions. And by that, you can enter in how many of those expressions you're going to look at, the number of harmonics, starting from n equals 1 on up to infinity. And on the left-hand side, you see the case for n equals 1, n equals 3, and n equals 10. The more and more terms you add, the closer and closer that the Fourier series represents the square wave. Another way to describe the coefficients is just by plotting them out. For example, here's it looks like a broken sawtooth type of waveform, right? And so the coefficients for Cn and Pn are given in a plot format where the height of each line spectrum is given in terms of the harmonic. So starting off with a fundamental at n equals 1 on up to 3 in this case for both Cn and Pn. Here's the same waveform, but now it's expressed using the exponential representation. And the plots are of the magnitude spectrum and the phase spectrum. Here are some common Fourier series representations. You see it for the square wave, the time-shifted square wave, the post-train, and triangular wave. And here are a few more for the half wave rectified sine wave, the full wave rectified sine wave, sawtooth wave, and triangle wave. So by using those common representations on the last couple of slides, what you can do is find one that's similar to get something that you actually want. So for example, let's say, the square wave was actually represented. That's the top graph, and the equation to that is given to the right of it. So let's say you know that, but what you really want is the second plot of the square wave, where it's sitting all above on the positive, the upper half of the graph, and instead of going to a height of A, it's actually going to a height of B. So what you do is this. You take the original x of t given on the very first equation, and what you do initially is you see that goes up to a height of A. It doesn't matter what A is, but what you want to do is normalize it. So you divide x of t by A. And if you look at x2, not the first expression, but look at the second expression. The second expression is where you can see that the A is on the denominator. Okay, and so that A being on the denominator, it normalizes it. So now if it's just x of t divided by A, the height of that square wave just goes up to 1, and that's it. So after that, then what you do is then you multiply it by b over 2. So that's the height where you want it next, to have it instead of going up to 1 and down to -1, you want to go up to b over 2 and down to negative b over 2. That's how you want the amplitude to go. And then once you have it there where it's symmetric about the y-axis, then you shift the entire plot up by b over 2. And that's the first term. Okay, so the first term, that b over 2, that's your DC offset, where you're getting the entire thing above the axis, the horizontal axis. Now for x3, that's a little easier to deal with because it goes up to A and down as far as negative A, so that's just like the very first plot at the top. But all you're going to do here is just shift it. And so instead of it being symmetric about the y-axis, you want it to be an odd function, like a sine wave, right? So what you do here is just do a time shift. So you minus the period over 4, t0 over 4, from the argument x of t. And then you plug that argument into every single term, and then you're able to generate your new your new function x3. So one thing you could do to simplify the number of computations that you need to do, you can actually cut them in half, is take note of the symmetry of the function that you're trying to represent. So if your function has even symmetry, then you could eliminate the b coefficients, right? Those are the ones that have the sine quantity in it. And if it has odd symmetry, then you can eliminate the DC offset as well as all of the AN coefficients, because they have the cosine quantity in those. In terms of the amplitude phase representation, the CN terms for even symmetry become the magnitude of AN, and the phases are going to be 0 if AN is positive, 180 degrees if AN is negative. And for odd symmetry, the CN terms will be the magnitude of the BNs, and the phases will be -90 for positive BNs and 90 degrees for negative Bn terms, coefficients. So that sharp ringing that happens at the vertices is called Gibbs phenomenon. And so Gibbs gets the credit, but I think it looks like what happened is after they named it after Gibbs, they found out that someone else discovered it 50 years prior to Gibbs. But Gibbs gets the credit. Now, there are ways to reduce it, but so far no one has found a way to totally eliminate it. Let's see how to do circuit analysis using Fourier series. It's a three-step process. First, you express the source in terms of an amplitude phase Fourier series. So the expressions are given right there below step 1. And step 2, you then determine a generic transfer function or frequency response of the circuit. So what you do there is you let the input be 1 cosine omega t, and in phasor notation that's just 1 because the phase is 0. So input is just 1, and so the output is just h of omega. And then on step 3, you just write down the time domain solution. So the output will be that DC term times h omega. Now that omega for the DC is at 0 because it's 0 frequency is a static case. And then for each of the quantities, you have to substitute in the right omega, which is the harmonic. So the first term will have just omega 0. The second term will have 2 omega 0. And then the next term will have 3 omega 0 inserted in there. And that will be the solution of the circuit. So let's apply that three-step process to an actual example. In this case, we're going to compute the voltage response of an RC circuit, and the input will be a square wave. We're going to use Fourier series. The circuit has a time constant RC of 2 seconds. In step 1, you express the source in terms of an amplitude phase Fourier series. So the series is given there, and below are the expressions to get the coefficients. In step 2, you determine the generic transfer function of the circuit. So what you do here, you can either apply KCL or KVL, and you'll end up with an expression in terms of V out and V in. So you manipulate your expression until you get the ratio of V out over V in. That would be your frequency response function, and for your input in phasor notation, it's just 1. And so it'll be V out over 1, and that will be your h of omega. For the last step, step 3, you just write down the time domain solution. So what you do there is you take your amplitude phase representation of your Fourier series and you plug in h everywhere. You just have to be mindful of what value of frequency you put in. And so that value of frequency, it covers what n is, right? So for the DC term, the n is 0, omega 0. For the other terms, they're the fundamental, where n is 1, and the harmonics, where your frequency is n omega for n equals 2 on up. Regarding Parsifal's theorem for periodic waveforms, Parsifal's theorem states that we can compute the average power of a signal in either the time or frequency domains and get the same result. On the left-hand side shows the average power sinusoids. You have a real sinusoid, not one of those fake ones you see around town, but a real one. Just kidding. It could be it could be cosine or sine, but the average power of that signal is going to be the amplitude squared over 2. For a complex exponential, which is complex sinusoid, real and imaginary, the power of that signal is the magnitude of a squared. Now, when you apply this to Fourier series, you get the three expressions in the green box. Each of those expressions are equivalent to each other. But you can see here that it's in terms of the DC power component and the AC power component for each one of them. There's really nothing new here, but I just want to show together the three types of Fourier series and their respective average powers. The last concept to talk about in this lecture is DC symmetry. DC symmetry is when the area above equals the area below. And so I have four functions plotted out. And so let's go through each one and discuss its type of symmetry. So the first plot just has even symmetry. There's no DC symmetry. But even symmetry is because you can take that right side of the plot and mirror it and reflect it through the y-axis. For the second plot, it has DC symmetry and even symmetry. So even symmetry is seen by reflecting it about the y-axis, and you get its mirror complement. It has DC symmetry because the area above is equal to the area below. On the third plot, it only has DC symmetry, right? But you can't see how you can reflect the right side of that plot about the y-axis or reflect it about the x-axis and get the left-hand side. So there's no other symmetry. There's no even symmetry, no odd symmetry, just DC symmetry. Now for the fourth plot at the bottom, that is DC symmetric. The area above is equal to the area below, and has odd symmetry, where you can take the right side and you can reflect it about the y-axis and then reflect it again about the x-axis and then get that left-hand side.